Hi everybody, welcome to your online physics lab. I just wanted to say hello face to face before you start hearing my disembodied voice over a PowerPoint to explain this first lab. So I hope you're all doing well. Let me know if you're having trouble accessing any of the things I'm sharing, or let your professor know if your professor is borrowing this video. Thanks a bunch. Okay, so this first lab that we are going to do is the resistor capacitor circuit, or the RC circuit lab. It's lab 10 in your manual. Now we're online. Yay, let's see how this works. All right, so the goal of the lab is going to be to study how the voltage decreases on a capacitor in a resistor capacitor circuit. So if our voltage is going to be decreasing, it means that our capacitor is going to be charged up when we start taking measurements. Now we're going to show that there's an exponential decrease with time, and we can talk about how quickly that exponential curve happens. So VC here is our voltage on our capacitor. V0 is that max voltage that our capacitor was charged up to. R is the value of our resistor, C is the value of our capacitor, and time is just the time it's been since we've been at that maximum voltage. So we're talking about the discharge of our capacitor here with this. So you're going to look for keywords like decrease or discharging the capacitor when you use this equation. Okay, so how do we arrive at this equation? Well, we arrived at this equation by doing a Kirchhoff's loop rule on this circuit. So when I do a Kirchhoff's loop rule, I like to start at the thing that is supplying the voltage. So in this case, it is this step function generator. And I'll draw a loop that starts at one side of that step function generator and comes around to the other side. Now in your textbook or things like that, you'll often see a source of EMF or a battery and a switch instead of a step function generator in this circuit. So that source of EMF has a certain steady voltage, and that switch is either going to be open, which means our voltage supplied is 0, or it's going to be closed, which means the voltage is this value other than 0. So in our part A of this lab, our value is going to be 4 volts. In part B, it's going to be 8 volts. So our step function generator kind of acts like that battery and switch, that when we've got something other than 0, our switch is closed, and when we've got 0, our switch is acting like an open switch. So we're going to see what happens to the voltage across our capacitor when we open that switch and our step function generator is supplying 0 voltage. And again, in this experiment, that's kind of an imaginary switch. So I like to draw my loops starting with the thing that's supplying the voltage, and then looking at all the elements of the circuit and saying that they are using up that voltage that is supplied, and when we get back to the starting point, we say it's equal to 0. In your lab, this equation is written instead with some things on the left-hand side and some things on the right-hand side. Both of those say the same thing, right? Okay, so here's where we get to remind ourselves the voltage across a capacitor at any given time is V equals, or Q equals V times C, right? So V equals our charge on the capacitor divided by C, right? So if we're discharging our capacitor, that charge is changing, right? If we're charging our capacitor, that charge could be changing. All right, and then the voltage drop across our resistor, that's just coming from Ohm's law. So that is our current through the resistor will give us our voltage drop across the resistor. Now, one further step we have to remember is that current is just how much charge goes by in a given amount of time. So our capacitor, when it is not fully charged, is gonna see charge being added to one side and taken away from the other side through that function generator or through that battery, right? So we are gonna see current through the resistor until the capacitor is fully charged. Then we see no current through the resistor, so no voltage drop across the resistor. So when our capacitor is fully charged or fully discharged, that value is going to be 0. Now, in intermediate physics, we go a step further and we go, let's go instantaneous current and take a derivative there. So let our time interval go to 0. So when we plug all that stuff into this equation, we get a differential equation. I don't expect you guys to already know differential equations. So just know that when we solve that differential equation, this is a valid solution for when V0, not V0, let's not call it that, our step function generator, our EMF, is equal to 0, right? So when we throw a 0 into that equation, our differential equation is going to look like 0 equals Q over C plus R times dQ dt. That's some really messy handwriting. But that's what that's going to look like. When we plug all that in, we're going to solve that differential equation. The solution to that is that lovely equation you've got on the previous slide. Okay, so moving on. One of the ways we're going to be able to measure if this equation is true is by measuring something called the half-life of the voltage. So the half-life of the voltage, we want to figure out how long, so a time, it takes for the voltage to decrease by half. So this is our voltage for the equation, right? Our equation for the voltage for our discharging capacitor. So when the capacitor discharges, we want to know when the capacitance voltage, that VC, equals half of our maximum voltage. So we want to set VC equal to half of our maximum voltage, right? So we're going to set it equal to V0 over 2. All right, so you can see that we could divide out of V0. If we divide out of V0, I end up with this equation here that's below my second bullet point. But you'll notice that the t, the time we're trying to find, is in the exponent. So we need to do something called a natural log to get that t out of the exponent. So if I take the natural log of both sides of the equation, I end up with something that looks like this, t over rc. So the natural log just got that exponent out of the exponent, right? And then natural log of 1/2. Now the other thing I did was I moved the negative sign over to the other side, right? I multiply by a -1. Now there's a cool trick with natural log that if I have negative the natural log of a fraction, that is the same as the natural log of the inverse of that fraction. So I can set that equal to 2. Now remember, I'm trying to find the time. I'm trying to find the half-life. So let's call this the half-life. We'll multiply that RC over here and then natural log of 2, right? So natural log of 2 is just a number. It's a number that's about 0.693, so about 69%. R and C, we know for our circuit. So if we know R in ohms and C in farads, we can find our time in seconds, right? Now remember, our capacitors, you'll notice when you read your book, or if you've ever gotten to play with electronics, capacitors are like picofarads or nanofarads, so that's a very small number. So we expect this to be a fraction of a second for our half-life, right? So we're gonna have to look closely at our graphs to be able to see that. Okay, so our experimental setup. On the right-hand side, you have a schematic of what our experimental setup is. On the left-hand side, you have an image of the experiment that I got to set up before I got kicked out of Franklin. Now, we're going to use our Pasco function generator right here as our step function generator. So I'm going to have to set that up to do a square wave where it looks like I've closed a switch and turned on a voltage at first 4 volts, and then opened a switch and the voltage goes to 0. I'll show you what that looks like in an oscilloscope in the next slide. So we're going to use that step function generator. We're going to plug it in according to our schematic to a capacitor. So you see the circuit board right here. I have plugged it in to this capacitor here. It's a very tiny device. It's labeled as 3,900 picofarads there. Then, according to my schematic, I'm going to come out of the capacitor and go into a resistor. So that's what this yellow cord right here is doing. It's coming out of the capacitor and into a resistor. And you can see here, right here on the board, you might even be able to read that in the picture. That is 47 kiloohms. That is my resistor. And then I'm going to go out of my resistor and back to my function generator. So then I've completed this whole loop that is shown on my schematic. All right, the other thing that we need to do is we want to measure the voltage drop across our capacitor, so we need a voltmeter. This right here is the voltmeter that we've been using so far this semester in the Pasco system again. So you'll see that voltmeter is plugged into my capacitor here on either side. So it's in parallel, just like I have it over here on the right in the schematic. So it's a really simple circuit. I'm bummed you guys didn't get to wire it up yourselves, but there's an image of how we did it. Okay, so here is an oscilloscope picture. So oscilloscopes are fun. They kind of show you the waveform if the waveform is changing over and over. It's really cool to see. Here's a screen capture of one anyway. So this right here in red that I'm drawing an arrow to, that is our signal generator, right? And so remember, our signal generator had this little picture that it was a square wave. That's our square wave. You'll see it's turning on here. It's at 4 volts, and it's turning off at 0 volts. And it is doing that pretty quickly. You can see the time scale down here. It is turning on and off at a pretty quick frequency. So I had to zoom in on that to be able to see anything interesting. Now, next to that, the other image you're seeing there that's kind of in that purple color, that right there is my voltmeter. So that is my voltage across the capacitor. And you can see here, there is an exponential increase, and here there is an exponential decrease. So remember, we're looking at this point right here where the capacitor is decreasing its voltage. So we turn off our function generator, or we turn off the switch right there, and you'll see it takes us a while for the capacitor to also reach 0 voltage. So it takes a certain amount of time for the capacitor to discharge. That's what we want to look at in this experiment. So in part A, we are looking at a capacitor value of 3,900 picofarads, a resistor value of 47 kiloohms, so remember your powers of 10 here, and we are at 4 volts. That is our max voltage that we have charged our capacitor up to. That is our resistor value, that is our capacitor value. So remember, in that equation for our half-life, the max value that we charged up to doesn't appear in that equation. So we'll come back to that. We're going to look at that, check that it's true. All right, so this is our oscilloscope picture. I want to instead look at a graph picture because I can use those coordinate tools that we've used before. So you can see here, I have a time and a max voltage measurement for my capacitor. It's just about 4 volts. It's not exactly. So I know that half of my max voltage should be just about 2 volts. So I have a time that it took to get from 4 volts to 2 volts. What I want to do is I want to measure that time difference, right? Because that is going to give me information on the half-life. How long did it take to get down to half the voltage? Now you can see here in this graph, I've switched my measurements to millivolts and milliseconds. The reason I did that was to give myself more significant figures, right? I have way more decimal places to work with. I have a little more precision. But you can also see I'm not exactly at 2 volts. I'm at 2001 and some change millivolts. That has to do with the precision of our measurement, right? Our Pasco system can only take data points so quickly, and so I missed the data point where it's exactly at 2,000 millivolts, right? Or 2 volts. So that's going to be one of our sources of error, is just how precisely we can measure our time and our voltage here. right? So in your lab, you're not only asked to see how long it takes for the voltage to go in half, but how long does it take for it to go in half again? So in half again, we go from 1/2 to 1/4. In half again, we go from 1/4 to 1/8. So I've hit those points for you. You just need to measure what is the time difference between those, right? Okay, so you guys can do that part in your analysis. All right, so in part B, we do the same thing. So we have the same circuit. We have a capacitor that is 3,900 picofarads. We have a resistor that is 47 kilo ohms. But now we're going to increase our signal generator so that our max voltage is 8 volts. So you can see right here, we are up at 8,000 millivolts, which is 8 volts. Right? You can see that our capacitor does reach that max value in the time we have our switch turned on. Okay, so what we want to see is when we get down to 1/2, so here would be about 1/2, right? Somewhere in there. Is that half-life time that we measure from here to here, is that half-life time the same? Right? Because that half-life equation that we came up with only had R and C in it. It didn't have that V0. So we're going to use the data from part B to double check that, right? So again, I've put it in a graph. I've got for you a max value and a last time at that max value. Your half of that max value, or as close as I could get. Your 1/4 of that max value, or as close as I could get, and 1/8 of that max value. All right, so then part C, we switch our capacitor value. So we're gonna see, does that switch our half-life time? And if you read the directions for part C, you actually also have to switch your frequency of how fast your signal generator turns on and off. So it's very faint in here, but you can see the signal generator is this faint blue line right here. So I had to switch that frequency because it actually takes a little longer for the capacitor to reach that max charge because it's a smaller capacitor. And if we were at the frequency that we had in part A and B, you don't reach that maximum value and you don't reach 0, which is a really interesting oscilloscope to see, but it's an extra complication that you guys don't need to be dealing with right now. So here, everything is set up as described in the lab, and we've measured our charging and discharging. And remember, our equations that we have in the lab are for this discharging section. And again, I've taken these measurements, our last time at the maximum value, our time at half the value, 1/4, 1/8 of the max value. So again, we're going to test out, does our prediction for the half-life match with our experimental values? What are some reasons it might not? We're ignoring our resistance in any of the connecting cables. We're assuming that our capacitor and resistor values are exactly as advertised. They are pretty good. They are those gold stripes that we talked about in the previous labs that tell us they're within a 5% tolerance, but they might not be perfect, right? And we also know, I've noted that our Pasco system isn't letting me get you to exactly 1/2 the voltage value and things like that. So I think this should be a pretty easy one to analyze for you guys. Just fill out the rest of your lab report or lab packet if that is what your professor is doing. Again, I'll share these images as well so you can see them close up and so that you can add them to your lab report if you need to. If you're having any issues with any of this, please let me know as soon as possible and I will help you out as I am able to. Thank you so much for watching all this. I'll try to continue to share these things as I finish them.